All right, these are problems 6 through 9 on review day number 11. And this first one gives us x plus 3y to the 1/3 equals y. Wants to know what dy dx is at 2/8. So we're going to take the derivative of this, which is 1 plus 3 times a third is 1. That'll be y to the negative 2/3 times dy dx equals dy dx. Now, sometimes we go through the process of trying to get dy dx by itself and bring it over to one side. I think with this negative 2/3, that'd be kind of clunky. So in my opinion, the best thing to do is just go ahead and put this point in right now, and we'll solve dy dx like it's a variable. So I'm going to put 8 in here. 8 to the negative 2/3 is equal to 1 over 8 to the 2/3, and the third root of 8 is 2. 2 to the second power is 4. So this 8 to the negative 2/3 is really 1/4. So we're going to have 1 plus 1/4 dy dx equals dy dx, which is like a 1 dy dx, right? So when I subtract this, I'm going to get 1 equals 3/4 dy dx. Just subtracting that fourth over there. So then if I multiply both sides by 4/3, I get dy dx equal to 4/3, which is d. Okay, so we do the derivative implicitly, get that line, throw the point in, and then solve for dy dx. It's probably the easiest way to go. For the next one here, we have the derivative of this. Now, we know what the derivative of x to the 5th is. It's 5x to the 4th. That's not a question. So when you look at your choices, you can throw a out right away. The other ones have the 5x to the 4th. The other one, it says 5 to the x. Now that's something we kind of skipped over that in class. We know that the derivative of e to the x is just e to the x, okay? With any other base, it's similar. It's going to repeat, but there's an adjustment that needs to be made to it, all right? And we won't get into the full scope of it. If you're interested, there's videos that show you all about it. But there's an adjustment that you have to make to the 5 to the x. And that adjustment is that you multiply by the natural log of that base. Now, we technically do it here. It's just that the natural log of e is 1. So that's why you don't really see it there. Okay. Now, if you knew, like, I know the power rule doesn't really apply to an exponential. You could have thrown that out. And as long as you remember that there's some adjustment that needs to be made, b doesn't have an adjustment, but d does. So even if you were unsure, if you couldn't remember exactly how it worked, with this problem, you could at least eliminate the other ones and get to d without any worry. Right. This next one here says, what's the limit as x goes to infinity? So if we let x get super big, the top goes to infinity, the bottom goes to infinity. So that's an indeterminate form. We're going to use L'Hopital's rule. Take the derivative of the top, negative 12x. Take the derivative of the bottom, 3 to the x. Try it again. Some of you can see where this is going to go right away, but we're going to get infinity over infinity. So do L'Hopital again. We're going to get negative 12 over 3 to the x. Now if I let x go to infinity, the top's going to stay negative 12, but the bottom's going to get super big. So if I take a number divided by something super big, that's going to go to 0. So anytime you have an exponential going against a polynomial, the exponential is always going to win in a case like that. And then our last one here gives us a graph of f prime, and we're told what these areas are. And we're said that the function is equal to 2 initially, and we want to know what the maximum value is. So this, again, these areas represent how f is changing. So if it started out as a value of 2 here, then once it gets to this point, it'll have added this 20, it'll have a value of 22. Once it gets to this point, that 6 is actually going to be taken away from it. So if we take that away, we'll be at a value of 16. And then when we get all the way here, we'll add 4 back. 20. We want to know what the highest value was, and that would have been 22. So not too bad.